Chapter 1, Reliable, Scalable and Maintainable Applications. The legendary Alan Kay once famously noted that the Internet was done so well that most people think of it as a natural resource, akin to the Pacific Ocean, rather than something that was entirely man-made. He posed a profound question: when was the last time a technology with a scale like that was so error-free? This highlights the immense engineering achievement behind the digital infrastructure we use every day. Modern applications have shifted paradigms. We are no longer compute-intensive, we are data-intensive. Raw CPU power is rarely the primary limiting factor for application performance. Instead, the real architectural challenges, the bigger problems, are centered around the sheer volume of data, the structural complexity of that data, and the high velocity speed at which that data is constantly evolving and changing. A data-intensive application is typically built by leveraging standard building blocks, which provide the commonly needed functionality for modern services. We utilize databases to persist state so that we can find information again later. We implement caches to store the results of expensive operations, effectively speeding up our read path latency. We use search indexes to allow users to filter by keywords, rather than scanning full data sets. We incorporate stream processing to send messages to other processes, allowing for asynchronous communication patterns. And we utilize batch processing to periodically crunch and analyze massive amounts of accumulated data to drive business intelligence. Thinking about data systems in the modern era. Many new tools for data storage and processing have emerged in recent years, and they often no longer neatly fit into the traditional, rigid categories we were taught. The boundaries are becoming blurred. For example, systems like Redis are now frequently used as message queues, while message brokers like Kafka provide durability guarantees that were once the sole domain of traditional relational databases. Increasingly, applications have such demanding or wide-ranging requirements that a single off-the-shelf tool can no longer meet all of its data processing and storage needs. Instead, the architectural work is broken down into modular tasks that can be performed efficiently on a single, specialized tool. And those different tools are ultimately stitched together by you, using application glue code. You are no longer just an application developer, you are a data system designer. In this series, we will focus on three primary concerns that are essential to the life cycle of any robust software system. Reliability. This means the system continues to work correctly, performing the intended function at the desired level of performance, even in the face of adversity, such as hardware faults, software bugs, or even human error. Reliability is the bedrock of trust. Scalability. As your system grows, whether that is an explosion in data volume, a spike in traffic, or increased architectural complexity, there must be reasonable, predictable, and cost-effective ways of dealing with that growth without requiring a total system rewrite. Scalability is not a single number, it is an architectural approach to managing load. Maintainability. This is about ensuring productive work for the engineering team over the entire lifetime of the system. It covers the ease of operation, the simplicity of the code base, and the ability to evolve the system to meet new, unforeseen requirements without accumulating technical debt. Maintainability is about minimizing the pain of change over the long term.